Hello everyone and welcome to this video. For today we will talk about conjugate operators, and on the next video we will talk about Hermitian operators. That is a set of operator with an important meaning in quantum chemistry, quantum physics, and so on. In this video, we'll introduce the concept of conjugate operator, and then we will solve some exercises from which we can observe how can we determine or obtain the conjugate operator of an operator. And for beginning, we will say that if we have an operator L and other operator M such that they satisfy the following equality. Here we have this inner product of L acting, for example, on the function phi, and here we have psi, and then it's equal to phi. Here we have M acting on psi. Then we say that L and M are conjugate operators, and we represent them as L, for example, equal to M dagger, or also M has equal to L dagger. For example, if we substitute this expression in this one, we have that we have now M dagger acting on phi. Here we have psi has equal to phi. Here we have M, and here we have psi. And if you remember the definition of inner product, you know that this term is equal to integral of M dagger complex conjugate acting on this is equal to M dagger complex conjugate acting on psi complex conjugate times psi. Here d of x, or I will write here in the whole space, has equal, and this term will be equal to phi complex conjugate M acting on psi, and we are taking the integration on the whole space. Actually, when we define the inner product, we normally we ask the functions phi and psi to be continuous, also on the whole space, also in infinity, must be univoc, continuous to give us the derivative of the function, univocal, which means that must give us the probability density, and also must be finite in infinite, normally equal to 0. Okay, and now we go on trying to solve. This is the definition of the definition of two conjugate operators, and now we will try to obtain or learning how can we obtain the conjugate operator of any operator. And for beginning, we have now on A, L has equal to C, with C a general complex number. And we know that if we have a Z number written as A plus I times B, then its complex conjugate is equal to A minus I times B, and if we take the complex conjugate of complex conjugate, we go back to the z number. Okay, for now we will this property or this concept, this definition, this expression is very important for us because we will apply now to try to obtain to the conjugate operator of L if L is equal to C. Okay, now we will use the definition of, okay, here we will put L dagger acting on phi. Here we have C has equal to phi L acting on psi, and this is equal actually to phi C, which is the operator for us, and psi there. And now, using the definition of the inner product, we know that here we have L dagger complex conjugate acting on psi, on phi, the complex conjugate times psi. And here we can consider, for example, we are working on x direction, and we have here d of x has equal to this term, which is equal to which is equal to phi complex conjugate times c times psi d of x. And remember that c here is only a number and is constant. Then we can take out from the integral, and we have now c integral of phi complex conjugate psi d of x. On the other hand, if we are finding here L, if L is equal to C, this means that L dagger is actually C dagger. And for here we can substitute here we can substitute here C, so that here if we have C has a number, then its complex conjugate or dagger complex conjugate must be also a number, so that we can take out from the integral. And we have here C dagger complex conjugate integral of phi dagger psi d of x. And now we have that this expression is equal to this one, so that we can simplify, and we get C dagger complex conjugate has equal to C. And now if we take here the complex conjugate, and also we must take here the complex conjugate, and we have now C dagger has equal to complex conjugate. This means that if we have an operator L has equal to C, which is a number, and yes, E is a number, then its complex conjugate will be every time also a number, but with the complex conjugate. Okay, we can go on solving the exercise B, which is L equal to U, and U is a multiplicative operator. Okay, this here is very important now to remember that if you have U has a multiplicative operator, this means that if we acting on psi of x, here it's equal to psi times U, because we are only taking the multiplication of U by psi, and also it's equal to psi times time u. Okay, now we can go on. Remember the definition. We have here u dagger acting on phi. For example, here we have psi has equal to phi u acting on psi, and from here we have u dagger complex conjugate acting on phi times psi d of x has equal to integral of phi complex conjugate u times psi d of x. Again, for now we can take this u operator from the right hand side of phi to the left hand side, and we get now integral of u of x times phi, or acting on phi, times psi d of x. And we can take this expression on the right hand side to the left hand side, and we have now u dagger complex conjugate minus u time phi star psi d of x has equal to 0. And now we know that this product is different to 0, which means that if this integral is equal to 0, then this expression must be equal to 0. And now we get that u dagger complex conjugate minus u is equal to 0, and then we have now u dagger complex conjugate has equal to u, and here we take again the complex conjugate, and here we must also take the complex conjugate, and then we write here u dagger is equal to u complex conjugate. Again, here we are concluding that if u of x or y or z or x, y, and z is a multiplicative operator, then its conjugate will be only equal to the complex conjugate of the operator. For now, we go on solving the exercise C, which is we have this operator, and we must search the conjugate operator of it, and also we must try to take or to obtain the complex conjugate of the nth derivative operator or differential operator. Okay, for now we have L has equal to d over d of x. The question is, what is its conjugate operator? Okay, again we must only use the definition. Here we have L dagger acting on phi psi has equal to phi here L psi, and from now we know that this is actually equal to L dagger complex conjugate acting on phi complex conjugate times psi d of x. Here we are taking the derivative on with respect to x, and we have for this term has equal to phi complex conjugate L. Okay, I will write now here L acting on psi d of x, and now we know that L is okay, we know that L is the first derivative of in function of x, and we have this has integral of phi star d of psi over d of x, and if you would take this integral by part, and we shows, for example, phi of x, star has equal to u, and d of psi over d of x has equal to d of v, then we have d of u has equal to d of phi star over d of x, and also we have here v has equal to psi, because we can simplify this by this and we get only the derivative of psi, and the integral of v will be actually equal to psi. And now, by definition of integral by part, we have this has equal to u times v, which is psi times phi star. From we are taking this integral, we can take this we are taking this integral from minus infinity to infinity, which is the whole space here, and we have minus v, which is psi, times d of u, which is this, and I will write this as d of phi over d of x times psi d of x. And from here, as we have mentioned it on the previous on the beginning of this video, actually when we has a physical with a physical meaning, every time we select psi and phi has continuous univocal infinite in infinite. Actually in infinite, we ask this function to be has equal to 0. Okay, and if psi and phi are equal to 0 on infinity, then we have this term has equal to 0, so that we have this only this part, and for now we have this has minus, or I can put in integral, we have minus d over d of x here. Okay, I will leave it like this, and here I have psi. And now we can go back to the original, not original expression, but we have here the original, or I can say, I wanna say the beginning, the beginning, or the initial integral, and then we have that this expression is actually equal to this one, or I meaning here L dagger complex conjugate acting on phi times psi d of x must be equal to the integral of minus d over d of x phi times psi d of x. And if we compare here, we can see that L dagger complex conjugate is acting on on phi star function, and also we can see here that these operators, this differential operator is acting on phi, so that from here we can conclude that then L dagger complex conjugate is equal to minus d over d of x. And if we take again here the complex conjugate of the left hand side, we must take also the complex conjugate of the right hand side, but we can see here that we are working with real numbers, or real real numbers or real variables, so that the complex conjugates of a real number or variables is equal to it's equal to it. And we have here L dagger has equal to d over d of x. And now we have arrived that if L is equal to d over d of x, then its conjugate operator is equal to minus d over d of x. Okay, now we go on trying to solve the next exercise, which is a matricial operator. Okay, for a matricial operator, if we have is D, no, yeah, if we have B has the matricial operators with element Bij, its conjugate operator is actually the transpose of the matrix, and then we take its complex conjugate, or we can also say it's equal to the complex conjugate of the matrix B, and we take the transpose of the matrix. I mean, suppose that we have, for example, B operator has equal to 1 plus I, and here we have 1, and here, for example, we have 3, or plus or minus 1, and here we have I, yeah, we have only I here. And to obtain B dagger, we must firstly take 1 plus I, 1, 3 minus I. We must take the transpose of this matrix, and then we'll take the complex conjugators of the resulting matrix, so that we know that the transpose of this matrix must be equal. We transform this line in column, and we have 1 plus I, and we get here 1, and also we must transform this line in column, and we have here 3 minus 1 and I here, complex conjugate. So that if you take the complex conjugate of each element of this matrix, we get 1 minus I, 3 plus I, here we have 1, and here we have minus I. This is actually the the conjugate operator of B. On the other hand, if you take the conjugate operator has equal to the complex conjugate, the conjugate operator of B, from here we can observe, for example, if we take firstly the complex conjugate, and we after that we take its transpose, then we have here 1 plus I, 1, 3 minus I, and here we have I. We have this has equal to 1 minus I, 1, 3 plus I, minus I, and we take its transpose, and we transform this line in column. We have 1 minus I, 1, and again we take this one, we have 3 plus I minus I, as we can see this actually equal to this expression. Okay, this is the only way to, or here it's B dagger is equal to J I complex conjugate, as we have saw here. Okay, we go on. Okay, we go on. On the exercise C, we didn't conclude because we must try to obtain L. If we have L has equal to d power n over d of x power n, what is its conjugate operator? As we saw here, if for example we take I can do something here. Okay, I must reduce this and take to there. Again here I can do the same thing. I will reduce and take. Okay, so that now I have more space here, and if we have L has equal to we know we can use the same procedures that we have used to solve this exercise to show that if L if you have B or M has equal to d power 2 over d of x power 2, its conjugate operator is actually equal to d power 2 d of x power 2. So that from here we can see that if L is equal to d, or if L is equal to this expression, then its complex conjugate will be equal to -1. Oh, sorry. Okay. Okay, then from here we can see that L dagger, which with L equal to this, it's equal to 1 minus 1 power n d power n over d of x power n, so that if n is equal to 0, we have only 1 here, and if n is equal to 1, we have L has equal to this, and we get its conjugate operator has equal to this, and we have n equal to 2, we have this has the operator, and we get its conjugate operator has equal to this, and we go on. Okay, for now we can go on solving the exercise E, which is L M operator. Or if you have this operator, which is a multiplier, we have has a multiplication of two operators. Yeah, and the question is what is its conjugate operator? And actually we can show that if you have M time sorry, if you have L time L, then its conjugate operator L M conjugate operator is actually equal to M dagger L dagger. Okay, for now for this video is everything okay. I hope you like to watch this video, and you can watch again the next video where we will talk about the Hermitian operators. Thank you for watching this video. Put like in this, share with your friends, and subscribe in our channel. Bye.